Hello, and welcome to the second video lecture for Chapter 5 on the topic of terrestrial worlds. If you haven't checked out the first video lecture, please do so. That's where we cover a lot of the broad general ideas about atmospheres, interiors, and surface features of terrestrial worlds. Okay, in this second lecture, we're going to go through the remaining slides from the lecture slideshow, and we're going to focus on just some individual facts about the planets and our moon. Okay, so that's the purpose of this video, is just kind of go through some interesting facts about the terrestrial worlds. Excuse me. Okay, so let's start with arguably the least interesting, which are the moon and Mercury. Okay, so first of all, let's talk about their atmospheres. Do they have atmospheres? Well, no, they don't. They really don't. And they kind of both look like the moon, don't they, right? Mercury looks like the moon. It's just a bleak gray planet, right? Lots of impact craters. In fact, Mercury has more impact craters because the moon has these large volcanic flows with fewer impact craters overlaid on top of them. Mercury doesn't really have those features. Mercury has more cliffs, although it's not really evident here in the picture. Okay, so what about the exospheres of the moon and Mercury? Okay, so the moon's exosphere, which extends high above the surface. Mercury's exosphere, much of which is escaping in this image, right? So it's just kind of being blown away by the solar wind. So sensitive measurements show that the moon and Mercury have extremely thin atmospheres. So the answer isn't as simple as just saying they don't have atmospheres, but they have very, very thin atmospheres. They're just a few molecules, okay? And those gases that make up the atmosphere largely come from impacts that eject surface atoms, okay? So it's not like the planets are trapping atoms in the same way that Earth and Venus and Mars trapped atoms early in the formation of those planets and kind of trapped an atmosphere by gravitational pull. Instead, the atmospheres of the moon and Mercury were created through impacts. Okay, so they're kind of leftover, freed up molecules. When say like an asteroid hit the ground, it didn't just stir up dust, but it actually vaporized some of the ground. Really kind of creating molecular gases, and those stuck around, right? Kind of drifting around in a very, very thin atmosphere. All right, which is would be imperceptible, right? You certainly can't breathe it. All right. So what about ice in polar craters? All right. So near the moon's north pole, the green circles indicate craters with ice. All right. So there is frozen water on the moon. Okay, on the moon's north pole. And near Mercury's north pole, purple regions have ice. Okay. So both planets, even Mercury being so close to the sun, do have frozen poles. All right, where you can find frozen water. All right. So what have we learned? Well, we've learned that the moon and Mercury have very thin atmospheres made up of particles ejected from the surface. Okay? So what about Earth's atmosphere? Very different story, right? Not just a very thin atmosphere made up of a few ejected particles, but rather complex. So how did Earth's atmosphere end up so different? Why does Earth's climate stay relatively stable? And how is human activity changing our planet? All right? So why did Earth retain most of its outgassed water? Okay, why does Earth, these are 4 important questions by the way, why does Earth have so little atmospheric carbon dioxide, unlike Venus? Why does Earth's atmosphere consist mostly of nitrogen and oxygen? And why does Earth have an ultraviolet absorbing stratosphere? Okay, because that's very unique to Earth. I mentioned in the previous video, Earth is the only terrestrial planet that has the ultraviolet absorbing stratosphere. Okay, so Earth's temperature remained cool enough for liquid oceans to form. The oceans dissolve atmospheric carbon dioxide, enabling carbon to be trapped in rocks. Okay, so we have a lot of water, and that water has an important role with carbon dioxide. Okay. Furthermore, most of Earth's carbon and oxygen is in rocks, leaving a mostly nitrogen atmosphere. Okay, so that idea of trapping all that carbon and oxygen in rocks played an important role, thus leaving a greater proportion of nitrogen in our atmosphere. Plants release some oxygen from CO2 into the atmosphere. All right, so it's not that we have no oxygen. We do have oxygen, but the atmosphere is mostly nitrogen. Okay. Furthermore, the ultraviolet light can break up diatomic oxygen, O2 molecules, allowing ozone to be formed. All right. Without plants to release O2, there would be no ozone in the stratosphere to absorb ultraviolet light. So it turns out that stratosphere First of all, it only is able to absorb ultraviolet light because of ozone. But where does ozone come from? Well, ozone comes from, a molecular process or a physical process with ultraviolet light combining with O2. But ultimately, where does ozone come from? Plants, because you can't have ozone without O2. And you can't have O2 without plants. There it is. Okay? You can't have ozone without plants. So that's why we have such a unique stratosphere, because of the hundreds of millions of years of plants living on the planet. Okay? So, right? So that's, life has an important role to play here. Okay? The ozone is life-sustaining, but also created by life. Okay? So why does Earth's climate stay relatively stable? Well, the carbon dioxide cycle has a big role. So atmospheric CO2 dissolves in rainwater. The rain erodes minerals that flow into the ocean, and those minerals combine with carbon to make rocks on the ocean floor. The subduction carries the carbonate rocks down into the mantle, all right, and the rocks then melt in the mantle, and the CO2 is outgassed via volcanoes. So that process retains a cycle. Okay, did you catch that? All right, atmospheric CO2 dissolves in rainwater, flows into the ocean, gets deposited in rocks. Rocks get pushed under other plates in plate tectonics. Those plates melt and then come back to the surface, coming up as volcanoes. Okay, so this figure really shows the process. Okay, all right. So that helps maintain. It's like a climate thermostat through carbon dioxide. Okay, so Earth's thermostat. The cooling allows CO2 to build up in the atmosphere. Heating causes rain to reduce CO2 in the atmosphere. So the planet warms up a little bit, then the CO2 levels adjust. Okay, if the planet cools a little bit, the CO2 levels adjust as well. So it's a natural adjustment process. Okay, so we can see then, right, a strengthened greenhouse effect will warm Earth up. Okay, and then the thermostat is the CO2 cycle. A weakened greenhouse effect will cool the Earth down. Okay, so let's start kind of with an external cause. Right, too cool. Too cool means less precipitation. Right, less rain. If the planet cools off, like during a glaciation phase of the planet, all right, well the planet cools off a lot. There's less rain. Right, think tropics have more rain. Cooler climates would have less rain. Well, that means that the rainwater dissolves less carbon dioxide from the atmosphere. So that means that a preponderance of carbon dioxide builds up because there's less rain to pull it out. Well, if there's less rain to pull the carbon dioxide out of the atmosphere, that means that we're going to strengthen the greenhouse effect and the planet will warm right back up. So it won't be too cool anymore. It'll be just right. Okay? On the other hand, if the planet becomes too warm, then precipitation levels increase, lots of big storms, lots of rain. That's going to pull carbon dioxide out of the atmosphere, and that means that it's going to get trapped in the oceans, eventually deposited in rocks, okay? And it'll take millions of years for it to come back out through outgassing, right? So in the short term, it's going to get trapped in rocks in the ocean, and that's going to cool the planet back off, okay? So is that going to happen with human effect to greenhouse gases? Yes, but in the meantime, right, for thousands of years, we're going to have much more extreme storms because we're going to have more precipitation. Okay, so long-term climate change. Changes in Earth's axial tilt might lead to ice ages, all right, because we definitely see lots of evidence of ice ages in the fossil record. Widespread ice tends to lower global temperatures by increasing Earth's reflectivity. Okay, remember that's called the albedo. The CO2 from outgassing will build up if oceans are frozen, ultimately raising global temperatures again. So all glaciation phases, all ice ages of the Earth do end because of that natural CO2 cycle. Okay? But what about human activity? Okay? So human activity has been very dramatic. We're dramatically increasing the CO2 levels at rates that the Earth has probably never seen. Okay? So human-made CFCs in the atmosphere destroy ozone, reducing protection from ultraviolet radiation. Human activity is driving many species to extinction. Right? We definitely have a mass extinction die out. Many species are disappearing. Humans' use of fossil fuels produce greenhouse gases that can cause global warming. All right? So Earth's average temperature has increased by 0.5 degrees Celsius in the past 50 years. The concentration of CO2, carbon dioxide, is rising rapidly. An unchecked rise in greenhouse gases will eventually lead to global warming. Okay? Absolutely will. Okay? So CO2 concentration. Global temperatures have tracked CO2 concentration for the last 500,000 years. The current CO2 concentration is the highest it's been in the last 500,000 years. Right? So in at least 500,000 years, this is the highest values we've ever seen. Okay? Most of the CO2 increase has happened in the last 50 years. Right? So there's an undeniable effect here, and it's going to have some serious effects on our climate, such as that more precipitation, okay? More extreme storms. Complex models of global warming suggest that recent temperature increase is consistent with human production of greenhouse gases. All right? So what's going to happen? Storms more numerous and intense, rising ocean levels, melting glaciers. So the sea levels have risen 20 centimeters in the past century, and they're expected to rise another 30 centimeters by 2100. Uncertain effects of food production, availability of fresh water, and potential social unrest. Absolutely. All right? The world will change. Okay? It will change dramatically in the next couple of generations. All right, so what have we learned? How did the Earth's atmosphere end up so different? The temperatures are just right for ocean water, okay? So really, I think that's important to reiterate that. I don't think I made that as clear as I could have a couple slides back. That, what was a key part of that process? Where does Earth have its unique oceans? Because that CO2 cycle needs the oceans to have that be the ultimate kind of endpoint for all the rainwater. And then, as that water flows in the ocean, it's then able to deposit in rocks. So having liquid water in general, liquid water in the atmosphere, liquid water in the form of rain, liquid water in oceans, that's the key. That's the key thing that maintains Earth's stable climate. All right, so the oceans keep most of the CO2 out of the atmosphere. Nitrogen remains in the atmosphere. Life releases some oxygen into the atmosphere. And all that play an important role. And it stays relatively stable because of the carbon dioxide cycle that acts as a thermostat. Okay? And any kind of thermostat process like that is very interesting, and I hope that is an idea that you can kind of focus on and make sense of yourself. And how is human activity changing our planet? Well, the destruction of the ozone, all right, higher rate of extinction, and global warming from the production of greenhouse gases. Okay, all right. So let's talk about some history of the terrestrial world, some specifics. All right. So what geological processes shaped our moon? Okay. Well, there are lunar maria. We've mentioned these before. They're smooth, dark lunar. The smooth, dark lunar maria are less heavily cratered than the lunar highlands. Why is that? Because they were formed after the era of heavy bombardment. All right, they are made by floods of runny lava. All right. So the formation of the lunar maria probably looked something like this. The early surface would have been covered in craters. This would have been around maybe about 3.5 billion years ago. All right, when the solar system was 1 billion years old. Large impact craters weakened the crust. So there are places where the crust became weak. At that era, the moon still had a molten core and a liquid mantle. And so lava was able to slowly bubble up to the surface over millions of years. The heat buildup allowed lava to well up to the surface, and that cooled lava would be smoother and darker than its surroundings and less cratered. And that's what we see, right? We see those big stretches of dark lunar maria. All right. What about tectonic features? Well, wrinkles arise from the cooling and contraction of a lava flood. All right. And the moon is considered geologically dead because geological processes have virtually stopped. Okay, so there's really no leftover heat in the interior of the planet. Here's an interesting idea. The Apollo astronauts left footprints like this one in the moon's powdery soil. Micrometeorites will eventually erase the footprints, but not for millions of years. Because there's really not many large meteorites left for large impacts. And so it's just going to be little tiny pieces of dust that will eventually destroy the footprint. But it will literally take 10 to hundreds of millions of years for that footprint to be erased. Because there's no wind, there's no atmosphere on the moon, and so it just stays forever, motionless. Okay? All right, so looking at Mercury, all right, close-up view of Mercury's surface showing impact craters in smooth regions where lava apparently covered up craters. All right, so cratering of Mercury. Mercury has a mixture of heavily cratered and smooth regions, much like the moon. The smooth regions are likely ancient lava flows, much like the moon. All right, here we have a spot on Mercury called the Rembrandt Basin, which is a large impact crater. All right, you can see it, huge one with smaller craters on top of it. The hollows in a crater, the crater floor created by escaping gases. All right, so there's evidence of escaping gases, which we can see in a different colored image, okay, showing non-visible light. All right. Furthermore, there's interesting tectonics on the moon. All right, so there's these long cliffs that run along the surface of Mercury, and they're thought to have been created by Mercury shrinking early in its history. So essentially, as Mercury's very large core cooled, the whole planet shrunk substantially, and thus leaving big sort of like cooling creases on the overall planet, creating giant cliffs. Okay? So what can we say about the geological processes that shape the moon? Early cratering is still visible. The Mare resulted from volcanism. What about Mercury? Well, we have cratering and volcanism similar to the moon, and tectonic features indicate early shrinkage. So the one thing you can think of is that the Mercury has giant cliffs on its surface, something that the moon does not have. Otherwise, a lot of similarities between the two. Okay, what about Mars? All right, what's the geology and history of Mars? What geological processes have shaped Mars, and what geological evidence tells us that water once flowed on Mars? All right. So way back in the 1900s, Percival Lowell misinterpreted the surface features seen in telescope images of Mars and thought that they were canals, right? Because he saw these long lines stretching across Mars. He thought, oh wow, there must be an ancient civilization, or maybe people live on Mars, right? And it seemed plausible, right? That there's actually life on Mars and intelligent, maybe human-like creatures building canals. But it turns out that's not the case, all right? There's not canals on Mars, but there are long cliffs and maybe previous rivers, dried riverbeds, all right? Here's a beautiful view of the surface of Mars, all right? So the amount of cratering differs greatly across Mars's surface. Many early craters have been erased, all right? Whereas not many early craters have been erased on either Mercury or the moon, okay? So here we have huge regions, right? For example, over here, right? Or here, huge regions without much cratering because there have been processes that have followed that have erased those early craters. There are still some kind of leftover areas of Mars that have kind of remained untouched, all right? So the highlands of Mars, okay? Mars has many large shield volcanoes. That lava certainly could have flowed over and erased the craters. Olympus Mons is the largest volcano in the solar system. It's about 10 miles tall, all right? The system of valleys known as the Valles Marineris is thought to originate from tectonics, right? So this is kind of like, plate tectonics like we have here on Earth, one plate sliding underneath another, okay? And what about geological evidence that tells us that water once flowed on Mars? Well, we see close-up photos of Mars show what appear to be dried up riverbeds, right? Doesn't this look like a flow of water? Okay, yeah, it does. And there's a lot of evidence of that, okay? Details of some craters suggest that they were once filled with water, right? Here's like a model that shows, what kind of, this is blowing up, so the vertical scale is exaggerated, but it really kind of shows what looks like would have been a lake and then a drainage from that lake, right? Because otherwise, why is there this cut that leads out of a crater? Okay. Furthermore, we see this alluvial river delta deposit. Okay. All really compelling evidence that water once flowed on the surface of Mars. Okay. It doesn't appear to currently flow. There may be some like melting of sort of like, muddy glaciers and some occasional water flows on the surface of Mars, but it certainly doesn't flow in the way that it once did hundreds of millions or a couple billion years ago. Okay. Furthermore, the Mars rover have found rocks that appear to have formed in water, right? So we have like, kind of these like river rocks, these spherical rocks that would have been eroded by water. This is what it looks like on Mars. Here's an example of basically the same type of rocks found on Utah in a dried up riverbed, okay? Mars rover have found rounded pebbles, characteristic of those found in streams. Look at this, right? That absolutely looks like the kind of thing that you would see built up in a stream bed. And here it is on Earth, okay? So pretty compelling evidence here, all right? It's kind of indirect, right? We're not literally, seeing the water, but we're seeing all these telltale signs of the water. Dark streaks in this image may indicate salty water that seasonally melts. This is what I was talking about, the fact that maybe there's still maybe some mud flows even today on Mars, okay? So what have we learned? What are the major geological features of Mars? Well, variation in cratering. Why is that? Well, because if water once flowed, water would have eroded cratering in significant sections. Perhaps those big smooth parts of Mars, to flip back to it, let's do that. Perhaps those big smooth sections of Mars were once oceans, okay? Furthermore, there's wind on Mars, so there's wind erosion that can, on a lesser scale, but can eliminate craters over time. And furthermore, there's a lot of volcanism, okay? So all that would create differences in cratering across the surface, okay? Giant shield volcanoes, already mentioned, and then evidence of tectonic activity. Is there current evidence of tectonic activity? Probably not, all right? So definitely, it seems that Mars is cooled down enough that it doesn't have the the big, moving plates like we have here on Earth. Okay, so what geological evidence tells us that water once flowed on Mars? Some surface features look like dry riverbeds. Some craters appear to be eroded, right, with the kind of like outlets of water. Rovers have found rocks that appear to have formed in water, and gullies and crater walls may indicate recent water flows. Okay, so let's talk about the atmosphere of Mars, right? We talked about surface. What about its atmosphere? What is Mars like today? Why did Mars change? All right, so Mars today. Well, early Mars would have had a strong magnetic field. If early Mars had a strong magnetic field, then that would have allowed for an atmosphere to be maintained. Okay, because a magnetic field redirects the solar wind, shown with these yellow arrows. That solar wind can strip away an atmosphere. So if it's not redirected, well, that's bad news for an atmosphere. So why would Mars have had a stronger magnetic field? Well, because it may have had a warmer core. Right? That warmer core would have generated a strong magnetic field. But since Mars is smaller than Earth and it has a greater surface area to volume ratio, Mars has cooled. So here we are at 4.5 years since the formation of the solar system, and Mars is cooled enough that its core is less warm, lacking convection, which means that it's basically lost its magnetic field entirely. Having lost its magnetic field, the solar wind is not redirected, but instead allowed to strip away the atmosphere, creating a cooler surface, okay, and a cooler interior, so no outgassing. Okay, well, the cooler interior means no outgassing, and the lack of atmosphere means a colder surface. So all these things have worked against Mars, have allowed it to turn into a planet that can no longer support life, even though it very possibly could have, right? Could there be fossils on Mars? Certainly, because there may have been life there, because it certainly could have had the conditions that could have been, beneficial for life. All right. So what about seasons on Mars? So the ellipticity, so that's just how elliptical its orbit is, of Mars's orbit makes seasons more extreme in the southern hemisphere. So there's a real asymmetry. Whereas here on Earth, we kind of have the same seasonal variation between the northern and southern hemispheres because our seasons are driven almost entirely by our tilt. On Mars, there's a bigger variation in one hemisphere than another because the planet's still tilted, but also it's quite elliptical, much more elliptical than Earth. All right. So the northern hemisphere winter is brief and mild, and the southern hemisphere summer is brief and warm, where the northern hemisphere summer is very hot. Right. All right. So here we have northern hemisphere summer is long and cool. Okay. Or well, yeah, long and cool. And then here's the most extreme one. The southern hemisphere winter is long and frigid. Okay. Okay. All right. So that's kind of an odd thing about the climate of Mars. Okay. Furthermore, ice on Mars. Yep. Residual ice of the solar polar cap remain during the summer, and it's primarily water ice. Okay. Carbon dioxide ice of the polar cap sublimates as summer approaches and condenses at the opposite pole. Right. So some of the ice on Mars is actually not H2O. It's just carbon dioxide, but there is actual water ice as well. Okay. And there's a lot of dust storms on Mars. So Mars today, it doesn't have a very thick atmosphere, but it certainly has enough of an atmosphere to support wind. And there's these big wind-driven dust storms that go across the surface of Mars, sometimes lasting for days on end. So seasonal winds can drive dust storms on Mars. Dust in the atmosphere absorbs blue light, sometimes making the sky look brownish pink. Right? We look at this, so we can see like during basically a planet-wide dust storm, the entire surface is obscured by the dust. All right, so calculations suggest that Mars's axial tilt ranges from 0 to 60 degrees, so it's much more variable than Earth's. Such extreme variation can cause climate change. So, on top of losing its magnetic field, perhaps there's just been wild variations in the climate that led to a kind of unsustainable climate, and eventually, the loss of liquid water. Alternating layers of ice and dust in the polar regions reflect these climate changes, so we can kind of look for evidence of that. Eventually we'll be sending probes to the poles of Mars. We haven't done so far, rovers, for example, and we'll learn even more about the mysteries of this neighboring planet. Okay? So why did Mars change? Well, Mars has not had widespread surface water for about 3 billion years. Greenhouse effects probably kept the surface warmer before that, and somehow Mars lost most of its atmosphere. Maybe it just lost it because it lost its magnetic field. All right? So the magnetic field may have preserved early Martian atmosphere, and the solar winds may have stripped the atmosphere after the field decreased because of the interior cooling. All right? So So that may have been the sad saga of Mars, is it only really kind of had a heyday for early in its history, and perhaps too early for complex life to evolve, and then it just became inhospitable after that. Okay, so this is a summary of the information. All right, but let's move on to Venus. I've kind of mentioned that Venus is a very interesting planet, an extreme case. So let's get into it. What geological processes have shaped Venus? Does Venus have plate tectonics? All right, well, here's Venus, okay? Venus is hot, incredibly, incredibly hot. Its surface is so hot that certain types of rock are able to melt, right? There's this big lava flows, right? Some things, we got volcanic peaks on the surface. We've got impact craters. We've got round blobs that are big volcanoes, right? But they're just kind of like big molten rock volcanoes, bubbling rock. It's like the surface of Venus is like the hell. It's just big boiling, outgassing fumes of rock and gas and flowing lava. Tectonic forces have fractured the crust, so there's big fractures. Round coronas probably made by a mantle plume, right? So a big like plume of lava coming up to the surface like a super volcano. All right. So this is all kind of these features of this super hot surface of this planet Venus. All right. So what's going on Venus? Well, its thick atmosphere forces us to explore Venus's surface through radar mapping. So we can't get the same kind of like telescope-based images like we had on Mars, where we had that beautiful map of the surface. Instead, we have to kind of figure things out through radar and then kind of artificially color everything. All right. But as I said, there's impact cratering, fewer than on Moon, Mercury, and Mars, because probably a lot of the volcanism has covered up at the impacts. All right. Lots of volcanoes, stratovolcanoes, shield volcanoes. Okay. Plate tectonics from stresses. Okay. Photos of rock taken by landers do show erosion. So there's features of erosion because there's types of rain, not like water rain, but there are liquids that rain down on the surface. Okay. And Venus does not appear to have plate tectonics, but the entire surface seems to have been repaved 750 million years ago. Why is that? Why is there no tectonics, even though Venus is about exactly the same size as Earth? Well, probably because of weaker convection, right? So there's probably not as much movement of the mantle, and so there's not that driving force, those convection cells to push the lithosphere around. All right, or perhaps the lithosphere is different. We're not sure, but there's something different about Venus that means that it doesn't appear to have active plate tectonics. Okay, so Venus has cratering, volcanism, and tectonics, but not much erosion. All right, and the lack of plate tectonics on Venus is a mystery. So you can have tectonics, which just means cracks, but not plate tectonics is different. That means like plates that are moving around freely from each other, like we have here on Earth. So the important thing is Earth is the only planet with plate tectonics, but it's not the only planet with tectonics. We saw evidence of tectonics, that is cracks on Mercury. We see it on Mars, and we see it on Venus. Okay, so it's good to distinguish between tectonics and plate tectonics. Okay, so what about the atmosphere? Okay, so surface, yeah, that's fine. Interior is interesting, but the atmosphere by far is the most interesting thing about Venus. What is Venus like today, and how did it get so hot? Okay. So what is Venus like today? Well, Venus has a very thick carbon dioxide atmosphere with surface pressure 90 times that of Earth. 90 times the pressure. That is hard to comprehend. I mean, you could go to the bottom of the ocean, the deepest ocean, where they have to build those special types of submarines that don't get crushed from the pressure, and it would only be about 10 times atmospheric pressure. 90 times is just incomprehensible. That is so dense, and that's just from a gas. Right? You think about high pressure from a liquid. This is high pressure from a gas. Okay. The slow rotation produces a very weak Coriolis effect and little weather. So the atmosphere is incredibly stagnant. There's very little wind. There's very little movement of the atmosphere. It's this thick, stagnant atmosphere holding in an incredible amount of heat. The thick carbon dioxide atmosphere produces an extremely strong greenhouse effect. Okay. So whatever light comes in, heats up the surface radiates infrared light, radiation, and that infrared radiation is completely trapped. It is opaque. The atmosphere is opaque to that infrared radiation. Earth escapes this fate because most of its carbon and water is in rocks and ocean. Okay, if all of our carbon dioxide trapped in rocks was freed and allowed to go in the atmosphere, we would end up like Venus. We would become a living hell. Okay, so how did Venus get so hot? Well, the reflected clouds contain drops of sulfuric acid. The upper atmosphere has fast winds that remain unexplained. Okay, so what happened? Well, one thing we think happened with Venus was a runaway greenhouse effect. So essentially, the higher temperatures increase evaporation and the warm air holds more water vapor in. And then that process just continues. So, right, because that means that then there's going to be more evaporation, additional water vapor further strengthens the greenhouse effect. Okay, so now there's more water in the atmosphere, and that means higher temperatures, which means more water evaporation, which means higher temperatures, which means more water evaporation, which means more higher temperatures, and so on, right? It just continues. It is a feedback loop. That's a term for it, because one leads to another, leads to another, leads to another. So eventually, all of the water is in the atmosphere. There's no liquid water left on the surface. It's all become a gas, and now the atmosphere is so thick with carbon dioxide that it's just holding in an incredible amount of heat, right? So the oceans evaporated. There almost certainly were liquid oceans on the surface of Venus at some point, but they completely evaporated. Imagine Earth's oceans evaporating completely and all that water just being in the atmosphere, all right? Carbonate rocks decomposed, all right, releasing CO2, all right? And that would make, that made Venus hotter and hotter and hotter. And the point here, look at this. If that happened to Earth, Earth would be even hotter than Venus. If the same thing happened, and it could happen, I'm not saying it's going to happen, but it could happen, Earth would end up even hotter than Venus and be completely ruined for life. All right? Okay? And that could explain what happened with Venus, right? It's a good model. What is the main reason why Venus is hotter than Earth? Okay? What do you think? All right, what do you think is the best answer here? Definitely the greenhouse effect. It's not that it is closer to the sun. That means it's a little bit hotter. Yeah, it might be more reflective. Like that could definitely lead to heat getting trapped or something. But the main thing by far is the greenhouse effect is much stronger on Venus. Okay, and just because of some tipping point, just because it ended up being a little bit stronger, and then more water got evaporated, and then there was no going back. That runaway feedback loop couldn't be stopped. Okay. So what is Venus like today? It has extremely thick atmosphere. The slow rotation means little weather. The runaway greenhouse effect made Venus too hot for liquid oceans, and all the carbon dioxide remains in the atmosphere. None of it is trapped in rocks or the ocean like here on Earth. Okay? All right, so a little bit more about the unique geology of Earth. How is Earth's surface shaped by plate tectonics, and why is Earth's geology destined from birth? All right, here are the plate tectonics. We saw this in the previous lecture as well, but here's a quick review. All right, so motion of the continents can be measured with GPS. We can actually see them moving at centimeters per year. All right, the idea of continental drift was inspired by the puzzle-like fits of the continents. I know it seems silly, but it's true, and they actually ended up working out. The mantle material erupts where the seafloor spreads apart. All right, so thin seafloor crust differs from the thick continental crust. The dating of the seafloor shows that it is usually quite young, quite a bit younger than the continents. All right, and the seafloor recycling comes from the fact that it's recycled through the process of subduction, because the seafloor is less dense it's denser, than the continental plates. So it gets pushed under the continental plates, it melts, and then it comes back up at volcanoes, but also gets returned to the surface at these mid-Atlantic or mid-ocean ridge points. Right, the Mid-Atlantic ridge being a good example of that. And so all that lava comes back up. So basically the mid-ocean ridges are just kind of long lines of small volcanoes where all of that melted seafloor crust is returning to the surface. Okay? So surface features, major geological features of North America record the history of plate tectonics. We can look for lots of evidence of that. The Himalayas formed from the collision between plates. Right, we had one plate crashing into another. In this case, the one plate is not sliding under the other, but they're just pushing into each other, creating a huge ridge, the largest mountains on Earth, the Himalayas. All right, the Red Sea is formed where plates are being pulled apart, right, basically leaving a gap, right, and water filled that gap. The San Andreas Fault in California is a plate boundary. Motion of the plates can cause earthquakes. So here we have plates that are sliding against each other rather than, because you kind of think about the cases, right? We have plates crashing together and making a big mountain. We have plates sliding under one another, or we have plates sliding side by side. And that's what's happening on the San Andreas Fault. All right. So plate motion means that the measurements of the plates can tell us that the past and future layout of the continents. So 200 million years ago, the continents were arranged quite differently. And 150 million years from now, they'll be arranged differently again, right? With the tip of Africa being in a much higher latitude. Okay. There are also hot spots like Hawaii, where basically lava is boiling up from the mantle. The Hawaiian Islands have formed where a plate is moving over a volcanic hotspot, kind of like a permanent hole in the crust. All right. Was Earth's geology destined from birth? Well, let's think about it, right? So here's that heavy bombardment during the first 500 million years. I mentioned that quite a few times. It's nice to actually see it in the figure. All right. A low leveling crater continued till today. And here we have the modern appearance of Earth. All right. So many of Earth's features are determined by its size, rotation, and distance from the sun. The reason for plate tectonics, however, is not clear. Right? Why is our mantle, particularly active? What has led to that? Why doesn't Venus, for example, have plate tectonics? Maybe it's because we're spinning faster than Venus, right? Okay, so and we really are quite a bit, right? Our axial rotation is 24 hours. Venus is like, I think it's like 200 Earth days or something. It's much, much longer. Venus is incredibly slow in its rotation. The measurements of plate motions confirm the idea of continental drift, and plate tectonics is responsible for subduction, seafloor spreading, mountains, rifts, and earthquakes. And that's also, kind of part of the amazing story of Earth, right? Because we've had all that movement. That's actually helped kind of the evolution of life, right? Because we've had, continents mix with each other and all these opportunities for survival of the fittest. And it's just a really fascinating tale. Was Earth's geology destined from birth? Well, many of Earth's features are determined by its size, distance from sun, and rotation rate. But there are some that really we don't quite understand, such as plate tectonics. All right, well, that's our conclusion of this second lecture video for Chapter 5. I hope it's been a nice, kind of a survey and study of the terrestrial planets. And thank you so much for watching.